Good morning and good afternoon, everyone, and welcome to our panel discussion, Why Distributed SQL's Moment is Now. I'm Brian Foster. I'm a content director here at PingCap, and I'll be your moderator for today's very exciting session. As data-intensive applications evolve, fueled by AI, global user demand, multi-tenant scale, traditional databases are starting to show their limits. Enterprises are looking for infrastructure that can scale flexibly, handle real-time workloads, and simplify operations. That brings us to distributed SQL, a technology that has matured significantly over the past decade and is now powering the next wave of intelligent applications. To help us explore why distributed SQL is reaching critical adoption, we've assembled a phenomenal panel here. First, we're joined by Sanjeev Mohan. He's founder of Sanjmo Advisory and a former research VP at Gartner, where he specialized in data and analytics infrastructure. Sanjeev has tracked the evolution of the database market for years, and his insights helped shape how enterprises evaluate emerging data platforms. Today, he advises leading vendors and end users on next-gen data architectures. Sanjeev, it's great to have you.
Thank you so much for having me. I'm excited to be on.
Yeah. Next, we have Dave Burgess, formerly VP of Data Engineering at Pinterest, and he's now a technical advisor. Dave oversaw Pinterest's transition from traditional sharded systems to modern streaming and distributed architectures at scale. His hands-on experience tackling the limits of database scalability and operational complexity gives him a practitioner's lens on why distributed SQL matters now. Welcome, Dave. Great to have you.
Thanks, Brian. It's a pleasure to be here.
Excellent. And finally, but not least, we are joined by Mark Donsky. He's a product manager here at PingCap, the company behind TiDB. Mark has worked across the database ecosystem at companies like Google and Cloudera. At PingCap, he's helping shape the future of distributed SQL, especially for AI-ready, multi-tenant, and cloud-native environments. It's great to have you, Mark.
Oh, thank you so much.
Well, again, thank each of you for joining us. I think this is going to be a really exciting discussion. But before we get started, for everyone tuning in around the world, please feel free to drop your questions directly into the chat window. We'll be sure to answer them during the Q&A portion at the end of the webinar. So please stay tuned. And with that, let's get started. So, distributed SQL, as I kind of mentioned, is again kind of maturing and I think kind of coming more and more into the limelight. The first question I think to kind of kick off the discussion, why is 2025 the tipping point for distributed SQL adoption compared to the past decade? And Sanjeev, let's start with you. What makes now different than all the hype and experimentation we've seen before?
Thank you, Brian. I have to say we are in this era where low latency, high throughput databases are not a luxury. We saw this trend actually take off a few years ago when SaaS products were starting to come up. But now we are very rapidly moving into the AI agentic architecture. In this architecture where you have multiple agents being deployed by an organization and they need to exchange information, they need to know each other's state, the context, we basically don't have a choice but to have these highly distributed databases that provide us this low latency and high throughput. We have seen some examples of that happening already. Just we are recording this in the month of June 2025. We had Snowflake Summit, we had Databricks Summit, and we saw the rise of these cloud native, highly scalable, highly performant databases. And I think that's one of the reasons why organizations are starting to invest in these distributed databases.
Excellent. Yeah. And Dave, kind of your perspective, how do you kind of, why do you see 2025 as the tipping point?
Sure. Well, it always takes many years for a new database technology to really mature and be ready for prime time and to be really scalable. And just in the last 5 years, many big companies within Silicon Valley have used these systems. And distributed SQL enables you to scale up from 0 to a very large scale and also includes other functionality like real-time analytics, some search functionality. And so now you can get quite a lot all within one package in one capability. And previously, you would have to cobble together systems. There would be large data engineering teams. They would need to put a key value store together with a relational database, with a search engine, with an analytics system. And there would always be data consistency problems between these systems. So this is almost kind of been solved now. And really, now that it's been solved and it's been used at scale with many big companies, it's really time for mass scale adoption.
Excellent. No, those are some great insights. And Mark, again, I want to bring you in too to kind of get your kind of take on why 2025 is the tipping point.
Yeah, sure. I'll start off by saying everything that Sanjeev and David said. I completely agree with what they're saying. There are a couple of points that I'd like to add just specifically for distributed SQL. So first off, modern applications are, as we've heard and as we all experience, getting extremely high scale. And along with this high scale, high availability and compliance are also needed. Distributed SQL is really one of the first platforms that really delivers on this goal. The flip side of it is historically, a lot of companies have looked at, it's pretty well understood that SQL is a great foundation with strong consistency and all of the expressiveness you get with SQL, but sharding is not a strategy. Sharding is very human intensive. It's very brittle. It introduces opportunities for outages and availability challenges. So sharding can't be a strategy. There has to be a better answer that just scales effortlessly. And finally, distributed SQL isn't early adopter territory. So distributed SQL goes all the way back, even before the Google Spanner paper that came out in 2012. So this is a very mature technology. It's proven. It's used by many of the leading applications that are out there, and it's ready for widespread adoption.
No, that's great to hear. And I think it's great to kind of see that maturity kind of taking shape and kind of seeing where that's going to lead us, I think, even in the coming months and years as well. I want to kind of shift a little bit, again, as we kind of, we're talking about kind of 2025 as a tipping point. I think one of those other big things that can be making it a tipping point is, of course, AI and the introduction of AI workloads. Next question I have for the panel is, how are AI workloads demanding a rethink of data infrastructure from the ground up? And Mark, I'll turn to you first. How are AI native use cases changing what we expect from the database layer?
So AI native use cases are changing the landscape in a number of ways. First off, the scale. The amount of data that databases have to bring in and store efficiently is just exploding tremendously. But the approaches for accessing the data is changing. The data has to be stored often for things like similarity searches and recommendation engines. So this often means vector embeddings and vector search for similarity capabilities. But the other piece of it is that all of the historical uses of databases, whether it's transaction-oriented, like shopping cart applications, or analytics-oriented dashboarding applications, remain. So AI is really just exponentially adding the burden or the workload on a centralized database. And I would say that's the big driver.
Yeah. No, that makes a lot of sense. And Dave, I'd love to get kind of your kind of take from an engineering perspective.
Sure. So I think there's several major drivers, especially of this last year with agentic AI and over the last 2.5 years with large language models, and previously to that with machine learning, all sorts of different use cases for machine learning. So one thing is that the agentic AI and large language model is going to drive even more data usage, more than would be through users directly, way more, 10 times, 100 times, if not more. And so systems really need to scale up to that. Another thing about agentic AI and large language models is they need structured data in order to be highly accurate. And if they don't have that, they're more likely to hallucinate. And so having structured data in a form that an agentic AI engine or a large language model can actually query will produce more accurate results at scale. And so distributed SQL really enables this to happen and be able to kind of map a large language model query into a SQL query that is very efficient at scale and with low latency and high performance.
Excellent. No, again a great compliment to what Mark was saying, and I think I think that kind of allows us really to kind of set the stage a little bit, but I think we can kind of now move into kind of some more macro trends and business drivers, and really I think kind of the next question that I want to pose to the panel is what macro shifts AI, analytics, compute as examples are putting pressure on legacy database systems today. And Dave, again, we'll start with you. I know you've had a front row seat to this. But what are the big forces creating cracks in traditional infrastructure?
Well, over I guess the last 10, 15 years, there's been more and more of a migration to cloud-based systems like AWS, Google Cloud, and also Microsoft Azure. And this is expected now to try and operate in the cloud with minimal operations, so have a very high availability. The total cost of ownership also needs to decrease. So you need to be able to automatically resolve a lot of issues and to be able to elastically scale up from small workloads to very high workloads. And so the legacy systems like Postgres, Oracle, MySQL weren't designed for the cloud initially, and they still have there's still after effects of that. And so having a cloud native database designed that uses the storage systems like S3 and AWS, uses the elastic compute capability to scale up to any scale that you want is really important. And moving away from things like sharding, as Mark pointed out, is really important. And also the ability to upgrade quickly. So these existing systems like Pinterest that would take a year to upgrade are 50 clusters of HBase and 100 clusters of MySQL, and just because of the complexity in doing it. Now with systems like TiDB, you can upgrade within a day or two. You take a day to verify the upgrade and then roll it out the next day. And so you're able to keep up to date as well, which is really important.
I can add to something Mark said. Dave said. I'll pick on his last point, which was this ease of upgrade. So basically, it's complexity reduction. What we are starting to see, 2025 is turning out to be quite an inflection point, quite an amazing year for M&As. And we are once again starting to see like Salesforce bought Informatica and other database companies are buying other companies. Why is that happening? It is because organizations want to reduce complexity. They want simplicity. We are starting to see there's a consolidation or rebundling that is starting to take place. They don't want to have a whole slew of products that do, let's say, search. Another one does vector. Another one does relational, and another one does geospatial, and so on. They'd rather have a full service application. Or it may be in data governance space, it may be in AI and ML space, but we see this rebundling that's happening. Some of it is actually a hangover from modern data stack that came during the COVID, the lockdown, where more and more companies were being funded, and during the ZERP area time when it was zero interest, funding was easy. So it led to an explosion of companies in every micro segmentation of the data and analytics pipeline. Now we are seeing reverse that's happening. Organizations are very clear. They're saying that we don't want to be spending time doing this, undifferentiated heavy lifting. It's AWS's term. We want to have our people focus on AI, focus on business, taking the business to the next level, whether it's competitive difference or new areas of revenue, rather than trying to upgrade a database, which is Dave's point. So they want this automation, and they want to focus on the business drivers and strategy rather than technology per se. And that to me is a huge macro trend that I see.
Yeah.
And if I may add one more.
Please.
In this trend, also Dave mentioned about migration to the cloud. That is actually very interesting because we see that we know data has gravity. Where is your data? Sometimes your data may be on-prem, sometimes it may be in the cloud. Organizations are also very clearly indicating we don't want to be moving our data all over the place. We want to bring AI and analytics to the data where it exists already. So we see there's a huge interest in hybrid solutions because the amount of data that AI needs to train a model is in hundreds of terabytes or exabytes, maybe petabytes. So with this volume of data, we want to keep the data where it is, bring AI to our data. So those are the two huge trends that I see these days.
No, that's great. And again, I kind of like how you again, definitely connected the dots there, which I think is super important. And I think again, kind of as we kind of kind of move it, into even our next question, that's kind of still within this area. We kind of come back to kind of distributed SQL, right? And the next question, that I have for the panel is, where does distributed SQL deliver measurable value in terms of TCO, licensing, or even operational efficiency? And Mark, I'd like to kind of turn it to you first. How are customers quantifying the benefits? Whether it's cost, simplification, or even consolidation.
Sure. Yeah, there are a couple of points I'll cover. The first, most obvious one is that you can leverage your existing skills. So your engineers that understand SQL will be productive with distributed SQL on day one. To give a very quick plug to Cap and TiDB, if you go to tidbcloud.com and create a cluster, you can start creating tables, start querying the tables, and reap all the benefits of distributed SQL. The same applies for every distributed SQL database out there, though. So productivity on day one without a steep learning curve is really, really important. But beyond that, in terms of higher level kind of cost implications, with distributed SQL, we often talk about scaling up, but we also have to emphasize starting small. Nearly every project out there starts as a small database, and most likely you don't have the resources to scale up to a petabyte scale database when you only have a couple of transactions per second. So with distributed SQL, you can start small and scale up as you need to, and your costs go up only as your usage goes up. Similarly, you pay only for what you use. So you typically don't have to provision upfront with core-based licenses, but you actually pay for what you use, and you don't pay for what you don't use. The final piece with distributed SQL is in disaster scenarios. So distributed SQL is typically architected from the ground up to withstand outages, whether it's zonal outages or regional outages with zero downtime, RPO of zero, RTO of zero. Distributed SQL is high availability that just works. It has built-in failover, typically multi-replication across availability zones. There's no custom tooling or really anything to do when there is an outage. So that also is a significant contributor to total cost of ownership.
Excellent.
And so, Mark, you mentioned scale up, but you're talking about scale out also, right?
Yeah. So scaling up and scaling out, it's helpful to describe both of these terms. So scaling up, let's just think. So actually, let's look at SQL as a whole. So typically with SQL, you run on a single machine. And if you want to handle more transactions or more data, you scale up. You deploy it on a bigger machine. Sometimes that's called scale out. Sometimes that's called scale up. But so at a certain point with standard single node SQL, you cap out because you can't deploy on a bigger machine. With distributed SQL, similar to NoSQL or HBase or Cassandra or any of these other horizontally scalable databases that aren't strongly consistent and don't fully support SQL, you can just keep adding more and more nodes. So that's kind of scaling out, because if you think about it horizontally, you're scaling out. With distributed SQL, specifically with TiDB, you have choice of the machine you deploy on. So you can deploy on a big machine or small machine. But I'd say the real benefit is the scaling out, where you can add more nodes horizontally or reduce the nodes. But you also have the option, if you have very complex queries, to deploy on beefier hardware. The real benefit of distributed SQL, I'd say, is more the scale out, though, and the scale in. That's my view, at least.
Excellent.
Yeah.
Dave, I'd love to get your take on this.
Sure. So for total cost of ownership, we did actually an in-depth study of how much our compute was, we were using HBase, 50 clusters of HBase before we moved to like TiDB. And we compared a lot of different technologies, about a dozen, and then whittled it down to TiDB. And in the end, it was performance and scalability and functionality that won. And so the performance was between 2 and 10 times faster in terms of transactions per second against our HBase cluster. And our total cost of ownership was reduced by something close to 80%. So a really high number. We had 5 people full-time working on just keeping HBase alive and maintaining it and patching it. And we thought HBase was coming close to end of life. There were less commits by the community in open source. And it was getting harder to adopt on new hardware, harder to apply security patches to it. And the new use cases required more functionality. And so we were building layers of functionality on top of HBase to do transactionality across multiple tables, to be able to do kind of analytics, to do some lots of updates. And so we were getting data consistency problems. And so by moving to a distributed SQL engine, we were able to have high data consistency, high performance, low latency, much lower latency than we had before, and a much lower total cost of ownership. And the amount of like maintenance we do now is far less. If you can spend more time enjoying doing development and building complex features on top of the database rather than building functionality that should be in the database. And so overall, the total cost of ownership made complete sense, as well as the operational efficiency became much easier, and the reliability was much higher. So, and the upgrade cycles were much higher, as Sanjeev and Mark have pointed out as well.
No, thank you. Yeah, that's again, good insights, kind of hearing kind of, how things are done at, at Pinterest, and kind of that transition there. I think it's really, really interesting. I like to kind of, shift it a little bit, and I think, get a little deeper. So again, kind of, my next question is, again, focused on distributed SQL, but really looking to get at kind of the differences. And the question is, how does distributed SQL fundamentally differ from traditional sharded architectures or NoSQL solutions? And Sanjeev, I'd love to start with you. What would you say are,
Okay.
some of the high level differences?
Okay, so let's just quickly take a look at what is sharding. So in sharding, what happens is your data is on, let's say, one system, but as the read request increase, you can one machine taps out in how much IOPS can it do. So then you say, okay, I'm going to move using some logic. I'm going to move some data into a different node, and then more data into a different node. So you start creating these you kind of horizontally distribute your data. Now with that, the reads go up. But the problem is that anytime you start sharding, there is some logic involved. Maybe there's a hash function or it's some range that you are using. So that logic adds an overhead, because at some point somebody has to say, oh, this read request needs to go to shard number 54. And it's a poor man's approach to scalability. In fact, when YouTube had started way back, that's how they did it. They basically had MySQL database, and they kept sharding and sharding till it became just too unbearable to add it. The new modern approach that distributed databases take is they use a consensus protocol. Because what we're trying to do is we're not just trying to scale reads, we also are trying to scale writes. So let's say Taylor Swift tickets go on sale, and then Dave, Mark, Brian, and we all.
I'm not going to go and see Taylor Swift.
Okay, fine. Okay, let's take Dave out of this picture. So we are all trying to buy the same ticket. So the inventory is in one place, and multiple writes are coming in. So the whole goal is, how do you do multi-writes? And that is really critical. NoSQL databases, when they first came out, they were very good at handling distributed use cases, but at the cost of transactions or consistency. They were not ACID compliant. So where distributed SQL comes into the picture is it is giving you multi-read, multi-write on the same data with solid transactional guarantees. In a mission critical financial services application, it is incomprehensible if we have writes happening and the data is inconsistent. So that is the first thing, and a lot of consensus protocols are used in order to ensure that we are committing the most recent last write. So time becomes an extremely important case. Distributed SQL databases, they're called distributed because they're geographically distributed. So if I have a node in North America, another node in Europe, another node in Asia, and we need to make sure the clocks are synchronized so we have a common understanding of time. And so we're talking about nanosecond precision here. Mark, correct me, you're the expert at this. So, so that is, so having consensus on time being of critical essence, having the ability to use a language that everybody knows, which is SQL. That's why it's called distributed SQL, rather than a graph language or a JSON-based language. Although nothing wrong with those, but SQL is a lingua franca. And in fact, even in AI, we are now having LLMs take a natural language and translate it into SQL. So those are some of the key building blocks. By being geographical, you get what Dave had mentioned, high availability, which means if something goes wrong in North America, I can fail over to a multi-region with no loss, so zero RTO, zero RPO. Those are the very critical building blocks that go into a distributed SQL, which you would not need in a monolithic single node relational database.
No, I appreciate that. Again, very, very nice, thorough response. Dave, I don't know if you have any additional things you'd like to add.
Well, I think I should correct the record that I would go to Taylor Swift in a heartbeat. She's an amazing singer and songwriter. But what I would add is that distributed SQL is naturally already in multiple availability zones within a region. So say the way you set it up is you actually have the data replicated in 3 availability zones at least. And so if any single node instance goes down, or if any single availability zone, which is a building, goes down, the system can continue to run. Whereas in traditional SQL, you're basically, if a node goes down, you have to recover that node, and there's a lot of work. Same with sharding. There are sharding solutions like Vitess and Proxy SQL that make it slightly easier to do sharding on top of the likes of MySQL, but it's still really complex, especially when you have to think about backup and recovery, and then the shards are changing over time as you scale. And so that all adds a lot of overhead to the team and a lot of complexity. So like Sanjeev said, the distributed SQL really takes care of this. It's like naturally designed to be able to scale. It's fault tolerant. It enables nodes to go down or to be rebooted or to be upgraded. So there are lots of advantages versus traditional SQL. In terms of like NoSQL solutions, NoSQL was created after the likes of MySQL relational databases, and that was it's basically a key value store that could scale up to billions of rows. But NoSQL is not necessarily transactional. And so having a transactional layer on top of that adds complexity. You also need you need the transactional part to have highly consistent data. So that's where distributed SQL came in, and distributed SQL added other capabilities such as analytics, real-time analytics, search as well. And so it's an evolution from where we started, relational databases deployed in your own premises, to NoSQL, which then went into the cloud, to then now distributed SQL that is born in the cloud, can do SQL at scale, at the scale of a NoSQL database, plus real-time analytics, plus some search capabilities. So that's it's really an evolution over time.
Excellent. No, good answer. Mark, again, anything you'd like to add?
Yeah, sure. I think there are two questions embedded here. The first one I can answer by saying I actually saw Taylor Swift in both Rio and Warsaw. But the second question about distributed SQL, I won't go through all the specifics that both Sanjeev and Dave have covered, but one of the key things that I look at, which I kind of alluded to in the previous question, if we look at SQL as a whole, the benefits that SQL give you is consistency. You don't get that with horizontally scalable databases like NoSQL, HBase, those kind of things. So SQL will give you consistency, but it doesn't scale. As I mentioned, you have the vertical scaling, but it caps out. And then you have to resort to these fallback mechanisms like sharding and so on. NoSQL easily gives you scale. There's no problem with that, but it doesn't give you consistency. The benefit of distributed SQL is that you get both. You get consistency and you get scale. And it's all in the same system. So everything that the other folks have said, 100% I agree with that. But I think at a very high level, you really get the best of both worlds with distributed SQL.
Excellent. No, thank you.
I don't think Taylor Swift is one of our audience members, but I think she should be listening to this. She should know about how important distributed SQL is to the performance of her concerts, So
You think it would be music to her ears, yes.
Good point. No pun intended.
Yeah, one other quick thing I just want to point out, there's a question here. We can certainly go into more detail about it, but I do want to highlight with distributed SQL, like TiDB, you absolutely get ACID compliance. You get strong external consistency. So we can certainly go into more detail about that on our website, as well as other distributed SQL systems you can look as well. This is a key benefit of distributed SQL. You have the ACID consistency. So I just want to quickly respond to that question, and we can go into more detail if folks want.
And I just want to make a quick point, since you mentioned, Mark, about other distributed SQL databases. There was a time when we went at length trying to explain what a distributed SQL is. But then something very interesting happened last December when Amazon AWS at reInvent decided that they're going to add DSQL, which is the distributed SQL component to Aurora database. So now all of a sudden, the whole space of distributed SQL has become mainstream. We don't really have to go explain what it is because AWS itself has jumped in with its 2 feet into this space.
Yeah, what comes to mind here is I've been working in distributed SQL for, I guess, about 6 years now. And I'd say for the first several years, we spent so much time speaking with customers and prospects explaining why distributed SQL was different. And what I have found now more effective is explaining why it's the same. Because in the end, yes, architecturally, you have horizontal scalability underneath the hood. But when you think about SQL, you have SQL semantics, you have tables, you have strong consistency. And what's really different with distributed SQL is that underneath the hood, you just have way more machines supporting it. But I absolutely agree with you. With Amazon's entry into here, this was a gap in their portfolio. And certainly we expect it'll take them some time to catch up, but they always do. And this really shows that distributed SQL is a critical piece of any modern application that's out there.
Excellent. No, thank you all for the discussion. I think it's definitely been pretty illuminating to kind of step through those pieces. I want to kind of step through and move to the next question. So the question I have again is what are the biggest myths or misconceptions about deploying distributed SQL at scale? And Dave, I'd love to start with you. What do you hear most often that's just not true or even oversimplified?
Sure. Well, I think some people think there's a lot of magic there, and there is some magic, but there's a lot of really top-notch computing decisions that's been made. But when you're as an application user, you really still need to think about your schema design. You can't just chuck things into a database and hope for the best. So you still need to think about, well, how would the underlying system partition the database, partition the tables? What are the primary keys? How would geo-replication occur? So across like 3 different availability zones in a region, or how would you do multi-region across one region and another region? So you still need to think these through. And the distributed SQL does simplify the operations, but you still need the database design discipline. So you know all that good learning you've done in the past, understanding how relational databases are designed will be applied to this. And so if you don't know how to do it yourself, then certainly reach out to a team that does know how to do it, because getting that right at the beginning is really important.
Sanjeev, I'd love to kind of hear from you on this one.
Yeah, so I see there are also a number of questions when people are questioning how does this magic happen. So out of the box, if you look at relational databases, they were not built to be distributed. They cannot be distributed out of the box. You really have to break the front end and the back end. By front end, you basically have either MySQL or Postgres, so you maintain that query layer. But behind the scenes, because it's writing to one location in the original code, so you need to break it down into a storage architecture where you write it to one copy, and then you instantly make replicas. And those replicas can be in different geographical regions, different availability zones, different regions. You get to decide where those are. And you don't return the commit till a certain number of replicas are written. And this is how now you've distributed your writes to different regions, and you can serve local reads much faster. So that is how the whole thing is architected. Now, to answer your question, what are some of the biggest myths and misconceptions is when people listen to this, they go, oh my God, this is too complicated. Do I really need this? And so the common myth was that you only need a distributed database for the most complicated use cases in the world, and most organizations don't really have to worry about it. But that's a misconception, because we are starting to see that almost all businesses are now global, whether they like it or not. Traffic is coming from different regions. They expect near instant response time. So we've actually gone to lengths trying to explain to people that distributed SQL should have been, in my opinion, should have been the norm. But it was not, because networks were slow, our architectures were behind. So that's why we went with monolithic single node solutions. But the reality is, with today's gigabit networks and high availability that we have across, we really need to think distributed as the default. If your business requires that kind of low latency on global scale. The second thing that I also want to point out is something that we have not yet talked about is, if I can have my rights distributed and written to different geographical areas, I can do more compliance and adhere to the data retention policies of different regions. And so that's yet another reason why I should really be looking at distributed databases from a fresh pair of eyes, rather than have this misconception that it's only limited use cases.
That makes a lot of sense. Mark, anything you'd like to add to that?
Yeah, I think that both Sanjeev and Dave have covered it, but the key thing for me is that there's this misconception that distributed SQL is really just for hyperscale or global applications. but teams can really adopt it for small applications and get predictable scale when they need it. Often you could be a gaming application and you have no idea if the game is going to be successful or not. And if it becomes successful and you don't scale efficiently, the game will be a disaster. But if you scale significantly upfront and the game isn't successful, then your cost dynamics are just completely out of whack. So distributed SQL is not just for the hyperscale applications. It's really, you can start small and grow only when you need to. The other misconception, and Sanjeev covered this, I think, but there's this view that distributed SQL is hard to adopt, but it really isn't. If your application uses SQL, it already works. Pretty much no rewrite is needed. Now, certainly with most distributed SQL, there are some subsets, like for example, user-defined functions or stored procedures typically aren't supported in distributed SQL, and there are other approaches. But for the most part, your application will run with minimal code change or no code change at all when you switch over to distributed SQL.
Yeah.
Mark, it's interesting you mentioned gaming as one of the examples. It's so interesting because these days with vibe coding taking off, gaming is becoming so easy. Like anyone can create a game. So if you are a developer and you're going to create, do vibe coding and create a super innovative game very quickly, it may go viral. And if it goes viral and your database sucks all the fun out of it, then there goes your vibe coded game.
Exactly.
So I think those are some of the very interesting new use cases that did not exist even 6 months ago.
Yeah. No, I like that a lot. And I think that also kind of cues up kind of my next question, which again is kind of moving in kind of the real world adoption. But I'd love to hear from the panel. Can you share an enterprise success story where distributed SQL dramatically changed the outcome? And Mark, I'd love to start with you. Obviously, again, kind of working for PingCap, even outside of that, your broader experience. I'd just love to kind of get your take.
Sure. Yeah. So I'll give one that's outside of gaming. I'll give one that's more traditional, like financial services. But you can go to our website. We have dozens of case studies there. So for anyone who's in the audience, if you care about your specific industry, I'm sure we have some case studies for you there. But the one I'd like to mention is Pingon Bank. Excuse me. They're a major retail bank, and they were using Oracle. But what they found is, like with most banks, their load on the database was cyclical. Typically, every month they would have customer statements that they had to generate, and they weren't able to run these overnight batch jobs efficiently because they kept having massive spikes at the end of the month, and they missed the SLAs, and they were doing constant firefighting. They just couldn't scale up or scale down in the way that they needed to support the business. They moved over to distributed SQL, TiDB. And once they did that, their statements were delivered in real time. All of the batch logic was gone. The system scaled up and down with demand. Whenever they had monthly high pressure kind of workloads, they would just scale up the system. And then at the end of that period, they would scale down to reduce their costs. It was the exact same application, but they had better performance and significantly de-risked their SLA targets.
No, I like that. Those are very good insights, and I'd love to turn to Dave. Again, I know we talked a little bit about Pinterest. Obviously, he used to work there. He played a pivotal role in kind of shaping the systems there. But I'd love to kind of hear a little bit from your end.
Yeah, one of our major use cases I mentioned before, we had 50 HBase clusters, and so Pinterest is a visual discovery engine. So if you've not used Pinterest before, it's a way to figure out what you love, what you like, and then visually through collecting images and putting them onto boards, and then make that a reality in your life. And so when people would collect images and put them into boards, sometimes they would have collected it, but it wouldn't show up in the search yet, or it wouldn't. They would refresh the board and they wouldn't see it anymore. And so there were data consistency problems, and this was across many different use cases. We had 300 use cases across our 50 HBase clusters. And so we started to bolt on extra functionality to try and compensate for this, because HBase is an eventual data consistent database. It's not transactional. not transactional across multiple tables. And so eventually we could not solve these problems, and we were constantly doing support and lots of production fixes and not being able to really fundamentally solve the problem. And so we needed a distributed SQL engine that was transactional, so that when we added an image, a pin to a board, it would be there. No matter how you would go and look for it, whether it was with search or whether it was going through a read operation. And by starting to look at various different distributed SQL technologies and try them out, we found that TiDB could actually work for our most complex use cases and be able to scale up from 0 to very, very high scale. And so there were many, many different use cases, and we took, you know, a long time to migrate all of these and by functionality after functionality. But it was far more stable, far more scalable, much lower latency, higher performant, and lower total cost of ownership, so we could upgrade really easily. And so the team has now been able to spend more time building functionality and really enjoying what they're doing, both the application team as well as the data engineering team, rather than being on call solving these endless production problems.
Thank you. No, those are great insights and kind of a nice deeper dive into the Pinterest story, which I think our audience is really enjoying. All right, I think we've come towards the end, and I have one more question for everyone. Again, it's been a super engaging discussion, but we want to just get started and kind of get that question going. So, what does the panel say? You know, what's the key criteria you'd recommend for deciding whether an organization is ready for distributed SQL? And Dave, I'd like to start with you. You know, what are the signals a team should look for, pain points, or even inflection points?
Yep. So I've gone through the whole life cycle of many different systems and adopting distributed SQL over the last 5 years. And I actually think starting off with distributed SQL in the first place is the best thing you can do. So if you're a startup and you're choosing technology, don't go and choose Postgres or MySQL. Start off with a cloud native database, a distributed SQL database that can scale with you and also handle lots of other workloads. Because typically you would start out and you think, oh, I need a transactional system. And then over time you think, oh, I need some search capability. So you add in a search engine and you try and get the data to sync between those. And then you say, oh, I need some real-time analytics. And you build a real-time analytics engine. And you need to, again, sync the data across those as well. And so if you start and choose the right technology from the get-go and start with a distributed SQL engine like TiDB, then it will save you many, many hours, days, months, years of work and frustration in the future. And it will scale up to what you need to. So that's the biggest thing. But now, if you don't have a green field and you haven't, which is the case for most of us, and you already have existing systems, so then it's a case of choosing: should I go and try and fix the system that has the major pain points and replace that with distributed SQL, or shall I start with a new use case and give that a shot? And that really depends on your scenario and your situation. But overall, the end game is to migrate everything to distributed SQL. You just have to choose which use case you're going to go for in the first place.
Perfect. I like that. Mark, I'd love to turn it to you. What do you say?
Sure. So I'd look at 4 indicators to determine whether you're ready for distributed SQL. The first one is obvious. Do you need SQL? This really rules out, are you looking at SQL? Or are you looking at NoSQL workloads? Are you running transactional workloads where consistency is important? Are you running analytic workloads where SQL semantics are really important and integrate really nicely with your overall analytics environment? All of the normal qualifiers for SQL should be considered, and this really rules out the NoSQL kind of world of things. There are a good number of workloads for which NoSQL is perfectly outstanding, but there are many of them where you should really be considering SQL. Once you have set on SQL, then you have to start thinking about how critical is availability. When it comes to a lot of these SQL workloads, zero downtime is, or near zero downtime is really absolutely vital to the application. So if your application can't afford any kind of downtime or degraded performance during a failover, or as Dave mentioned, upgrades, that really gives you the need for high availability, which distributed SQL is built from the ground up to support. The third point is how much operational overhead is going into the workarounds to support your current infrastructure. So if you already have landed on SQL and you've already determined that availability is paramount, how many, like, are you doing a lot of manual sharding to handle the scale, or do you have a lot of replication scripts built to support failover in the event of a zonal outage or a regional outage? How many folks are doing capacity planning spreadsheets and trying to figure out how to provision to support anticipated workload? Distributed SQL eliminates all of that complicated manual work, and you get scale and fault tolerance right out of the box. And then the fourth point is how global is your application? Sanjeev spoke about this a bit, but if you're deploying across multiple regions or serving users or want to serve users closer to the edge, or you have data residency requirements, that's often a big one. Traditional databases will often struggle with these kinds of needs, and distributed SQL handles these kind of complexities natively without splitting your architecture up at all.
Excellent. And yeah, thank you, Mark. Really appreciate that.
Sure.
And Sanjeev, I'd love to turn to you to kind of wrap us up here.
Yeah, so Brian, thank you so much for asking this question, because I wrote a whole document on this and I used TiDB as my guinea pig to explain what are the criteria, it's like key criteria to evaluate a distributed database. That blog is on my Medium site, which is sanjmo.medium.com. The way I explain it is, anytime I have to do the evaluation criteria, I divide it into two halves, functional and non-functional. Functional is, what is it that you want to do, and can the database even meet your needs? Like maybe you want to do vector searches, or maybe you want to do operational. 90% of the use cases are operational, transactional, like banking, and so on. But then some needs are for analytical. So OLTP versus OLAP. Interestingly, in TiDB, you can get both OLTP and OLAP in the same package, which again reduces that complexity, the need to ETL data between OLTP and OLAP. So that's a functional. And then the non-functional, all the things we've been talking about: scale, high availability, performance, and then most important, the total cost of ownership, or TCO, because you can get all kinds of bells and whistles, but what is the price you are paying? So I'll wrap it up here. So there's functional and non-functional. Those are the key criteria categories.
Excellent. Well, again, thank you, everyone, for, again, this amazing discussion. Again, I think we covered quite a lot of ground, which I think is great. But it's been a great conversation. And it's clear that distributed SQL is really no longer a fringe choice. It is becoming the foundation for high scale, high resilience, and even AI systems. Let's check it out. Let's see if we have any questions from our audience. I know we've been answering at least a few of them as we go. I'm looking at one now. Again, from an anonymous attendee. Seems that this individual is again kind of new to TiDB, and it's more of a I think a clarification. And Mark, I think you might be the best one to kind of answer this one. TiDB is row oriented like RDBMS, column oriented like an OLAP, or more Cassandra like type. Can you just kind of maybe just really quickly just clarify kind of our architecture, the various pieces, and what goes into it?
Yeah. Before I even answer that, I see there's one question asking what TiDB is. So let me just go through that quickly. I think during this panel, we've really focused on making sure we talk about distributed SQL as a whole. Yes. But just to be super clear for the folks attending, I'm from PingCap, which is the company behind the distributed SQL database called TiDB. That's TI, like titanium, DB database. And it's available on all the leading cloud providers. You can also deploy it in your own environment. We have an open source offering. Now, what sets TiDB apart from other distributed SQL is specifically what Brian just mentioned. We're absolutely a transactional database with strong consistency, strong external consistency, meaning that you can have a global application and you can have lots of people doing, as Sanjeev pointed out, lots of writes, and all the writes will be done in a consistent way, making sure that one doesn't overwrite the other. If you're doing debits from different locations, you won't overdraft the accounts through bad code, all that kind of stuff. But what sets TiDB apart is not just, and transactional is typically row-based storage, is not just the row-based transaction orientation. We also have a columnar store that goes alongside that is replicated synchronously with any of the writes to the database. And you can designate this at the table level. So I'm covering this in some detail, but let me explain what that means. You likely in a transactional database have a subset of the tables that you want to run large scale analytics on. And pretty much every transactional database, any database either does transactions well or it does analytics well, but they don't do both well because transactions typically require row-based storage and analytics typically require column-based storage. What TiDB does is it has both of those, and you can designate specific tables to say this is worthy of analytics, and you just have to alter the table and say something like alter table set TiFlash. TiFlash is our term for the columnar store. Once you do that, then any writes to those tables that have been designated as both row-based and columnar-based storage, any writes to the table will automatically update the columnar store, making it suitable for very high scale, highly efficient analytical type queries. So I think that answers the question. So TiDB, underneath the hood, you designate a table level, which tables you want to run analytics on, and then we automatically behind the scenes synchronize a columnar store that you actually don't even have to access. Just when you run the queries, it knows to use the columnar store for efficiency.
Excellent. No, yeah, thanks, Mark, for going a little bit deeper into that. Again, it's a good kind of, again, kind of putting a practical spin, which we touched on, but I think focusing on it makes a lot of sense. Just looking through our questions here, I know we're getting close to the time here. Again, I'm seeing a question around kind of, again, total cost, TiDB's total cost compared to OLTP and OLAP pipelines. Again, maybe a question that, again, may be difficult to answer here, but we can definitely follow up with additional information after that. So definitely appreciate that. One other question here that I think is from the same attendee, but a kind of clarifying use case. Is TiDB suitable for geospatial work? Again, I'm not certain about that, but Mark, I'm curious to kind of hear your thoughts on that. Oh, I think you're on mute.
I'm sorry about that. TiDB does have some basic spatial functions that have through its full MySQL compatibility. So you can certainly store and query simple spatial data using like geometry columns. But things like spatial indexing, large scale kind of spatial joins, for these kinds of applications, it typically would make sense to use a database that's specifically oriented for geospatial. We do have customers that do use TiDB for geospatial kind of capabilities, but it's always helpful to look exactly at the workload. The benefits you get with TiDB beyond like the basic spatial is that you'll have the transactional consistency, you'll have the analytics, you'll have the vector search. So there are broader capabilities you can take advantage of, but for pure geospatial and kind of advanced kind of workloads, you likely would want to look at specialized systems for that.
Excellent. Well, no, well, thank you, Mark. Really appreciate it. Again, good answer. And yeah, it looks like right now we are at about time, which again is, I want to, again, thank everyone for attending today's talk. Really appreciate it. Want to thank, again, our amazing panelists, Sanjeev, Dave, and Mark. Thanks again for joining, answering, and kind of providing all the in-depth knowledge and sharing it with the rest of us. Really appreciate it.
Thank you so much. Take care.
Yes. Thank you all.